Aqueous solutions can be further broken down and described as either being a strong, weak, or non-electrolyte, depending on the properties of the substance being dissolved. So when you see the term electrolyte, notice the electro at the beginning, so similar to electricity. So describing something as a strong, weak, or non-electrolyte also indicates the degree to which that solution can conduct electricity. So when we look at a strong electrolyte, so this will include ionic compounds, and our strong acids and bases. Strong acids and strong bases. And we'll talk about how we identify those in a later lesson. But right now what we're looking at is we look at NaCl, and what we see is that it completely dissociates in water, which means it completely breaks apart into its ions. So NaCl breaks apart into Na plus and Cl minus. So if I were to look at a solution of salt water, what I would see are sodium ions and chloride ions. I would not see units of NaCl, and I wouldn't see any of those because it completely dissociates. Notice that we have an arrow here that only goes in one direction, indicating that the solid dissociates into the ions. When I look at weak electrolytes, what I see is that this is a weak acid, so we'll typically see this for weak acids and weak bases. So HF, I'm going to tell you at this point, is a weak acid, and it's going to partially dissociate, meaning a small percentage of these HF molecules will break apart into the ions. So we'll have a small percentage of those molecules as H plus ions and F minus ions. The majority of these molecules will stay as HF in that solution. In this case, notice that we have a two-directional arrow. This is called an equilibrium arrow. And what that represents is that the reaction is going in both the forward and the reverse direction. And we'll talk more about equilibrium later. For right now, know that it indicates that this is an equilibrium process, that the reaction can proceed in both directions, and that it represents a weak electrolyte because not all of the HF will dissociate into my ions. The last classification is a non-electrolyte. And so an example of this is sugar, table sugar, also known as sucrose. And so sucrose, to an extent, will dissolve into a certain amount, will dissolve in water. And so what we see is that we have a molecule here, a molecular compound, and it shows a one-directional arrow because it's all dissolving in water. But notice that the chemical formula of the product looks exactly the same as the reactant because it stays completely intact in that solution. So we don't see any breaking up into ions. And we tend to see this for molecular compounds. So just like many other things, there are exceptions to these general rules of ionic, the weak acids and bases, and molecular compounds, but this will be sufficient for our purposes. Now, when we look at our strong electrolyte, we have lots of ions, meaning we have lots of charge carriers, meaning these are excellent conductors of electricity. When I look at weak electrolytes, they are very poor conductors of electricity. There are some ions present to help transfer those move electrons, but not very many. So it's going to be a weak conductor of electricity. And a non-electrolyte is going to be a non-conductor of electricity. So HF, if you've heard about it, can be a very nasty acid, but it's considered weak because of its dissociation into ions is at a very low percentage, not because of the damage it can do. So strong, weak, and non-electrolyte indicate how much something dissociates in water and therefore the strength of its electrical conductivity. So when we look at something like water, typically we say water is a non or very, very, very weak electrolyte, but the instructions given during a storm are always to get out of the pool. And that's because there are other things present in the water that are going to be excellent conductors of electricity.